Entendi. Teste, teste. Ok. Esse é o PDF ou é o PowerPoint? É o PDF. Então pronto. Não, volta, volta. Aí. Testando. Tá, tá. Qual o pointer é o do meio, é? É. Ok. Yeah, because was made by PowerPoint and, and not to be a discovery the next slide, I prefer to use the PDF. Anyway, I'll talk a little bit something different that the Magnums, but in the end, we can see a convergence. I came from the Federal University of Pará. Pará is in north of Brazil, belongs to Amazonia, or you prefer the gate of Amazonia. And the motivation of this work is to design the ultimate device. Here's a line of carbons with the one single atom in the center using as device with no chemical bond. And we want to see when you put a potential, the electronic transport through this material. Also, to see without this device, without a single atom. And actually, the first motivation was experimental work of a few collaborators, but they have some issues, and the results was not so good at time. But we continue with the simulation. Also, not only a one-dimensional system, but a quasi one-dimensional system. You use a nanotube, and again with one single atom and no atom at all. Here's the simulation when you apply a bias in the system, and the current and the conductance. And we can see no response until reach a value, and then the system start to conduct. This is known as a device known as a thyristor. In opposite a transistor, when you have the plateau in the current, here we can reach the plateau with a bias. After 0.9 applied bias, the system explodes. So it's a really a thyristor device. And if you take off the single atom in the middle, here in the same scale, you see no signature at all. But if you make a zoom of this scale, you have a little bit signal of 10 minus 7 nanoampere. And more than that, in the same value that the system with the sodium, or upper to 0.6 volts. Here comparing the both systems, and when we submit this paper, one of the referees say, okay, your simulation is very good, but I want to see not with only this distance, but you need to vary this distance. The idea is very good, but you know, every dot that you can see in the figure, it's a full simulation. And if you vary the system, it's here I put only with 3 angstroms and 4 angstroms this distance. But your simulation, the time consuming of simulations, it's a lot more. I just put here this result, but this was a second work, and I say, okay, the idea is very good, but it's a different work. But here I took only 3 and 4 angstroms. We did a full variation from 0.1 angstrom from 0.12 angstroms. And you see the qualitative results, it's the same, but meaning after a specific value, in this case 0.6 volts of bias, the system starts to conduct, but the quantitative values change significatively. The first one, the 5.9 angstroms, we have the current 10 minus 7 nanoampere. With 4, we have something like 2.5, the maximum, and 3, we have 250. It meaning that the qualitative result is there, and there is a physics behind after one point. Então, let's see exactly the science behind that. Here the transmittance with the applied bias and the energy. You can also the density of states with the applied bias and the energy. You can reach only states in this triangle and this one. Here is not able to reach these states. So you can see exactly the transmutation. It's only, you have only signal exactly showing the value up to 0.6. And the density of states increase actually with the similar value. Meaning that the physics is correct. And here, unfortunately, we have a move, very didactical one, showing that, but are not able to show you. But the physics is here. This is the high channels. What that means? Means the high channels. High channels, you take all the orbitals, not only the frontier molecular orbitals, but you take all the orbitals that they contribute for the specific applied bias for the electronic transport. Here for no bias, you have only a small quantity in one electrode. But after 0.6, 0.7, 0.9, you can see clearly that you have the high channels in both sides of the electrodes. And for the distance without the sodium, here is 10 minus 7 nanoampere, meaning that it's very difficult. You have the signature, but it's very difficult to make the transport, but is there. If you take, as usual, unfortunately here was the video, but the physics is already in this chart. If you take to try to understand with only the frontier molecular orbitals of the systems, here the high occupied molecular orbital and lowest unoccupied molecular orbital of the both systems, you are not able to explain why the system conduct or switch from off to on after a specific value of applied bias. This previous methodology was a very new one that we implemented, because in general in the area, you only look for the orbitals close to the highest occupied and the lowest unoccupied. Okay. Let's see the second system. Now it's, you know, the leads are the same infinite, but so you can say it's a quasi one-dimensional system. And here's, we can see the nanotube in the front view. And you can see there is a twist between this one and this one. You can see the 5 carbon atoms are not put exactly front to front, because experimentally sometimes, or most of the times, it's difficult to see. So we want to also investigate with this spin, or this degree, in this case 90-degree angle, change in the conductance. So let's see what happened in this case. In the first one, including in the device, the single atom, in the first view, if you look only the current with the applied bias, you may say, okay, it's resistive behavior. But if you look the differential conductance, you can say that is not true. You can see the resonance effects, meaning the similar effect of a transistor without gate. What that means, a transistor without gate, meaning that we have only one window of operation. Because as we know, the regular transistor, the gate, when you apply a voltage in the gate, you only shift up and down the signature of the current and the conductance. In this case, the transistor only 2 gates, the left and right. You have only one operational window. More than that, the first region is like a resistive. You can see here in the conductance. After a resonance, and you can see it's a very smooth behavior of similar as a FET. Comparing with the system without the atom in the middle. It's the red one. Again, in the same scale, you have no signature. But if you give a deep look, the signature is there. It's more than that. The physical behavior, it's a little bit different. Also, we have a behavior of a FET, but you can see here drops, meaning we have a region of negative differential resistance. So you can say in this device, of course, here's is 10 minus 12. It's very smooth behavior. It's not an error because our simulation error is 1,000 of this value, 1,000 layer, lower than this value. So we can see the system works as similar FET with the single atom, plus we have in a different operational region, a negative differential operation. So, meaning two devices in one. You learn science and Portuguese too. As you can see here, tension and energy. Tensão means bias, and energia means energy. I'm sorry, I took, you learned two subjects in this lecture. Good, right? Good, good. So here's the applied bias by energy, the transmittance and density of states of the first system. And again, you can prove why only after a value around the 0.6 volts that you have possibility of transmission, meaning that increase the values of your current. One interesting thing that we don't know exactly what that means. In the density of states, we have some islands of states, and these islands are important for the transport. And we published this without a very strong explanation, but we see sometimes this behavior, but we don't know yet what is happening there. We know for sure that it is islands of status, you can reach it, and they significantly contribute for the electronic transport. But it's all that we can say for now. This is not the first system that we have this behavior, and probably there is a physics in there that we We don't know yet. Again, here the eigenchannels explain not only the frontier molecular orbitals, but the all contributions for the specific applied bias. In the opposite of the real one-dimensional system, because we start with a very small bias the system conduct, you can see that in the Heim channels, meaning that the cloud, it's already reaching the central atom and then going to the other lead. In the case with no atom, in the device with no atom, because the current is very, very small, 10 minus 12, you are not able to see the cloud in both leads. Meaning, what we can explain here, the very small quantity of electrons contribute for the transport. Again, here was a place for very didactical showing increasing, but the physics is already there. Okay, my time it's over, but I think more 5 minutes only to show the idea. It is not it is a second part of the works that we do in our group. This is almost 1D system because it's a nanoribbon. Of course, I think everybody knows the graphene, but it's not a graphene. This is a new one. It's the phagraphene. If you're not, if you don't know the area, in the last 5 years, we have more than 15 different 2D structures, allotropous of carbons comparing to graphene. The main goal to study this kind of materials, yesterday I was talking with a few colleagues about the cars, electric cars. And I know for sure the electric cars of today, it's one thing, meaning it's a no green technology at all. Because to do the battery with the technology that they use the lithium, to construct for one single car, you need 10 pools, Olympic pools of water to extract the lithium and make the final battery. And this water, it's very difficult to make it pure again for one single car. And this is important because they first start with the graphene, sheets of graphene in lithium atoms between the sheets. And the atoms stays, in principle, inside of the hexagon. But after a few cycles of discharge and charge, the electrons move. And these new ones, allotropous, you have, this is one case, and you have 3, 6, 7, not more hexagon, and the lithium is more stable. And they already did a test that the system could be stable, the charge stable by 10, compared with graphene. So that's why in the last 5 years, not a few ones is experimental one, the synthesis ones, most is theoretical. It's very good calculations of molecular dynamics that can make the system stable. And in this case, we performed to use using the similar methodology as presented before, the transport. More than that, we included to compare substitutional impurities. Is a boron and nitrogen. Of course, my time is over, but I will switch for the, we did the same kind of calculation with the different sizes of the nanoribbon. It was a very good, but I will, the same methodology, but I want to switch for the last one, this one. This is a very new methodology that we incorporate in our simulation, is the inelastic transport, the phonon energy of the system. And I learned here, and in a few papers when eggs invite me, and I say, okay, I don't work with magnons, but let's see what we can do. And I learned that one way to detect magnons is look for this quantity, the phonon energy. And in this case, of course, I take a look, and of course, there is no magnum in this case, because it's only carbon, hydrogen, boron, and nitrogen. But if you have a toy model and or experimental setup that you can put some magnet atoms and make some mixture with this 1D, 2D materials, and you want to compare with ab initio / no equilibrium grain function and as inelastic transport, and compare with your methodology, we are here. And we show a lot of where is the inelastic transport, is where exactly in the almost 2D or 1D system, because it's a nanoribbon, appears when we have all this methodology. Here's the acknowledgement. Actually, I put here only the people that specifically work in these papers. But as we know, the groups, they change through time. Today in my group, we have 2 associate professors, 1 adjunct professor, 1 postdoc, 5 PhD, 3 master, and 2 very important undergraduate students. And I'm sorry for the delay. Thank you.
Thank you, Jordan, for this interesting talk. Actually, I can give the first start for a question if you don't mind checking. Uh, so you already partially answered my question, but before considering a spin atom or molecule, I think based on what I saw, you can have a molecule instead of an atom, right? You considered. Can you explain better what is the formulas that you're actually using behind the calculations?
Okay. First, we need to do a DFT calculation of the structure. And of course, in DFT, you can, it depends of the functional that you want to use. This is very important. If you want a magnetic one that take this into account, we can choose that, right? For this case was not necessary, and the base set in general. Then after that, we needed to apply the bias for the system. So we use green functions to do that, right? And in general, it's like that.
Right.
Okay.
Thank you.
Thank you.
We have more questions?
So in the first part of the talk, where you had the 1D versus quasi 1D systems, so in the quasi 1D case, you have like a molecular lead. The lead is a little bit more complex, right? And so there, the electrons in principle can couple to some sort of phononic modes in the lead, because the lead has this kind of, could have some sort of vibrational modes, I guess. Is that sort of included in your simulations? And if so?
At time that we did the second system that we included the phone modes, it's a new methodology that we implemented. When we did for this system, we did not take into account the phone modes, because in this case it's an inelastic kind of the transport, and we want to see on the elastic ones. And but today I can do that. We can.
Question?
So you're in the very in the linear regime. It's our equilibrium in this. Can you do non-equilibrium as well, like a higher voltage?
Well, what do you mean as a high voltage? We always go up to 1 volt, right?
Yeah, well, non-linear response in the sense.
Yeah, the non-linear response is the Phonon energy.
And how does it work? How does it enter in your DFT calculation? Because you're coupling DFT plus Green's function for transport, right? So how do you implement that in when you have a bias applied? Then how does that enter in the DFT? Is it like a linear? What is the potential drop, and how do you put this in?
Well, I can. I don't have by head because it's a huge catch, but we include a extra term of the potential, right? That simulates the bias, right? Because we change the potential of the system.
But then I remember at some point, people would do this kind of calculation many years ago, and there were a lot of problems, because once you apply a bias, you shift.
You cannot apply a bias, for example, 10 volts, because we have some limitations. For example, the leads necessarily should be metallic ones, right? And you cannot use leads, for example, semiconductor ones, because otherwise you are out of the methodology. You need it's like you take the electron here, but it's already full. It's like the instantant full of electrons.
So on the leads, left
the
and
leads.
right, you basically keep the potential constant. You just basically raise the
You
level
raise
here,
up,
but you're not
exactly.
really accounting for any, distortion
You,
that would be
I know what you want to. You don't have something like a noise or something like that, some variation. No, it's always constant. You take the electron, but it's like the instantaneously full again,
Mhm.
right?
Okay, thank you.
Thank you.
All right. I think with this, we thank the speaker once again. And see you in a few minutes after the coffee break. Yes. Yes, please.
I think you can take